Okay, we will start the today's session. Uh, so the topics that we are going to cover are we start with the arc length and surface area. Then we move on to the convergence of the series. Okay, not series, but basically a sequence. So convergence or divergence of the sequence. And most of the problems we do are related to the convergence of the sequence, because the assignment has more weightage towards it. So we will do more in this area. And also another thing is the arc length and the surface calculations are more or less similar. So we will do one sample problems, and then the other things you can do almost similarly. Okay. Okay, so let's start with the arc length, finding the arc length. So I will write here. So let's start with the example. So let's say you have a function f of x, which is 2x 3 by 2. So the question is to calculate the arc length of f of x over the interval 0. Okay. So over this interval, you have to calculate the arc length of this function. So the formula to find the arc length formula is right here. Start with the solution. So if you have a curve which is given by o equal to f of x, which is a function of x, then the arc length to find the arc. So basically, let's say you have a curve like this, some f of x, and you have this a and b, and you want to find basically the arc length means you have to find the length of this, right? So if you want to imagine the arc length, you see it like you have a thread over this f of x, and then you just straighten it and measure with the ruler. So that's kind of like the arc length, and the formula to do that is this is done in the class, so I'll just use the formula. This is the integral over a to b square root of 1 plus f prime of x square dx. I mean, of course, it's assumed that your function is twice differentiable, etc. Okay. So this is the formula. Now we have the f of x, which is equal to 2x cube by 2. So we have f of x, which is equal to 2x 3 by 2. So we want to find f prime of x first, and then you have to take a square and then add 1 and take the square root, right? So let's find the f prime of x. So f prime of x is nothing but 3 by 2 into, yeah, so this 2 will be there before 3 by 2, and x power 3 by 2 minus 1. So which is basically 3 times x power 1 by 2. Okay. So now we want to find f of x square. Sorry, f prime of x square, which is nothing but 3x. Sorry, not 3x, 9x. Okay. Now the arc length is easy to compute. We'll write arc length is equal to integral a to b square root of 1 plus f prime of x whole square dx. So this is nothing but integral from, okay, in this case we want to find the arc length from 0 to 1. So the limits are going to be 0 to 1 square root of 1 plus 9x. Okay. Now what remains to do is to just integrate this and then substitute the bound here. So to do the integration, we are going to use the substitution. So let say u equal to, see, because if the 1 is not here, it's not very hard to integrate. Only problem is this 1 kind of comes here, and we substitute and then kind of try to remove this 1. equal to, let's say, 1 plus 9x, and du will be just dx, right? Now we substitute it here, and also when you make this substitution, you have to see how the limit changes also. So let's draw a table and then see what happens. When you have x goes from 0 to 1, but let's look at u. When x is 0, u is 1, and when x is 1, u will be 10. Okay, so now you made the substitution, you also have to change the uh, limits here. Okay, or what you can do is you substitute, I mean, you do find the definite integral, do everything, and then uh, substitute this back. Okay, so there are two ways to do. We'll do both. Let's say this is method 1, let's say, where we change the limits here itself, and let's proceed with this. So now you have an integral. So wait, du is not exactly dx. Du, see, you have to see here, right? Du equal to 9 dx. Okay. So if you want dx, it is 1 by 9 du. Okay. So now we substitute everything back. So arc length now. This will be from integral from 1 to 10 square root of u, and instead of dx you will write 1 by 9 du, right? So this is what you have. Now the 1 by 9 comes before, and then this is 1 to 10. So u power 1 by 2 du. So this is 1 by 9. U power 1 by 2 plus 1 by 1 by 2 plus 1. This you have to integrate from 1 to 10. Okay. So this is nothing but 1 by 9. U power, I think, 3 by 2 by, here again you have 3 by 2. Derivate this from 1 to 10, right? So you just have to evaluate, and this you can find, I mean, this will be 2 by, so this will come on the other side by 2 by 3, but okay. So this is 2 by 27, u power 3 by 2. So this evaluated at 1 from 1 to 10. So this will be 2 by 27, 10 square root of 10 cube, basically, minus 1. Okay. So this is the answer. I mean, if you want, you can compute to the decimal places, but I will leave it here. Okay. So to compute the arc length, all you have to do is take the first derivative of it, take the square of it, and then you just add it. Okay, add 1, take the square root, and then integrate. And so there's not much to do. Only thing is, now you have to know how to do the integration, and which we have done previously. So I assume that everybody knows that. So the arc length computation is very simple. You don't have to do much. So let's move on to the surface area now. So surface area is also similarly easy. There is not. Uh, I mean, the thing is, it's almost similar. I mean, almost similar means, so if we solve one problem, then every problem is almost similar. Okay, it's not almost similar to arc length. So let's go with the surface area. So I will start with the first problem here. So before that, maybe I will write the problem. So what we are actually doing here, I will just recall. So let's say I have a function like this. Okay. Now what we are doing is this function is, let's say, f of x. Okay. What we are doing is we kind of rotate this function. So you have a function, and imagine you are in a 3 dimension, and you are rotating this function here along. I mean about this x-axis, let's say. Okay. So if you rotate this function about the x-axis, then you will get uh, something kind of looks similar to a parabola, right? So you will get something like this, and you want to find the area of that. So you will get something like this, and this curve, let's say it goes on the other direction also. So it's kind of like a cylinder, but not exactly the cylinder, because I mean it's not a perpendicular line, right? It's curved. So what you're going to trying to find is find the surface area, basically the just the outer area of this, not the entire volume, but just the outer layer. Okay. So if you want to imagine, imagine like you cut one part of it, and then you can kind of roll back. So you will get a sheet of something in R2, and you can uh, kind of find the mm, surface area of that. It's kind of the similar problem, but now uh, you're seeing it in a 3D. Now you want to find the surface area of uh, this particular object here. Okay. And when you have something like this, so now you can also see this is basically I'm rotating along x-axis. Similarly, I can rotate along the y-axis also, but there also the formula is kind of the same. Means basically you write the function here. The function is y equal to f of x. There you write the function as x equal to f of y, and then you can do the same thing. So let's write the formula for here, and this is also done in the class. So we'll just write the formula. So the surface area is nothing but integral from a to b, 2 pi f of x square root of 1 plus f prime of x square dx. Okay. So this is the surface area formula, and we are just going to do the integration. That's all. Okay, so let me write the problem, and then we will try to do it. So let's start our second problem here. So let's say I have a function here, which is f of x, which is, let's say, square root of x. Okay. Now what we are going to do is we are going to rotate this square root of x. If you draw the square root of x, it looks something like this only. Now what we are going to do is we are going to rotate the square root of x along the x-axis. So that generates uh, a region. And if you want me to draw, I can draw it. It goes something like this. Uh, okay. Maybe that's not a correct description. Okay. And similarly here also it goes. Okay. Probably I have to probably I will put a dotted line here. Okay. So what you are trying to find is basically the outer surface of this. So this is what we are basically trying to find, right? So here from where let's say the limit. So we have the function here, and we want to find the surface area. I will write the problem fully. Find the, maybe I use the different color. Find the surface area of the surface generated by revolving the graph of x around. Okay. So basically what you're going to do is we are revolving the graph and then we are finding the surface area. But let me just write. I mean, you need to find a bound. I mean, we have to have the bound also. So let's say this is the function over the interval 1 to 4. So basically, we just want the surface area of this piece. Okay, just this piece. So let's say this point is 1 here, and this point is 4. Okay, so let's. So here you see what all you have to do is you have to find the uh, first derivative, and then just substitute the formula and integrate. You got it, right? So there's not much to do. So let's start doing it. So we'll start the solution here. So here we have f of x is equal to square root of x, right? So we compute the first derivative. So which is also x power 1 by 2. So here if you compute it is 1 by 2 x power minus 1 by 2. So this is the first derivative. So it is 1 by 2 root x. Okay. So now we got the first derivative. All you have to do is just to square it. So this will become 1 by 4x. Now you have to find the square root of 1 plus f prime of x square. So this will be 1 plus 1 by 4x. This is what you have, and you have to take the square root, right? Now let's find the surface area. So surface area is nothing but integral a to b 2 pi f of x square root of 1 plus f prime of x square dx. So this is the formula. Now what you're going to do is just substitute here. So this is the integral from 1 to 4. So because we want to find the surface area from this range, right? From 1 to 4 only. So this will be integral from 1 to 4. 2 pi. So your f of x is square root of x. Square root of 1 plus 4 by, 1 plus 1 by 4x dx, right? So this is what we have. So the question is, okay, now so far so good. Okay, how do you integrate it? Okay, so this was the question, right? Now all you have to do is just integrate. There's not much to do here. But integration is not always the easy thing to do, but but all you have to do is integrate. Okay, so first thing what you observe is we have both square root, so you can so you have this formula square root of a square root of b is nothing but the square root of ab, but the formula may be written other way. So I mean other way, it may be square root of ab square root of a square root of b, but you see here, so you can combine these square roots 1 to 4 2 pi. So the reason you can combine the square root is when you do that, you can kind of take away this x that is coming in the denominator. We don't want it to be in the denominator because it might create a problem. So this is x plus x by 4x. So you can cancel out the x. So this gives you 1 to 4, 2 pi square root of x plus 1 by 4 dx. Right now we kind of came to the previous case, right? It's almost the previous case. If you look here, where we done it, yeah. So this is 1 plus 9x. So it's the same square root. I mean, there's 2 pi in the front, but that doesn't matter. It's a constant, right? So it's almost the same case, and we are going to do the same idea. So we are going to substitute here, and then solve it exactly the same. I mean, when I say exactly the same, it's not exactly the same, but the idea is the same. There's no new idea here. All you have to do is do the substitution and you will get it. So let's start with u, substitute u, which is equal to x plus, let's say, 1 by 4. So then du became just dx. Now we can substitute everything back in. So this will become integral 1 to 4 2 pi square root of u. Okay, I don't need this big square root. So this is square root of u du. But see, I made error here, so I cannot. I have to change the limit also. Okay. So here probably what we do is instead of doing the limit here, we do the other way, where we first find the definite integral, then we can substitute things back later. Okay. So instead of finding the with the limit, what we do is first we integrate it, then we'll substitute the limit back in. Okay. So probably I will write that way. I mean, you can do both ways. So since we did the last problem the other way, we will do this problem differently. So you can take, now I'm finding the definite integral, or basically I'm doing the antiderivative. So this will be nothing but 2 pi. So you can integrate it. So this will gives you, wait, just 1 minute. It's 1 by 2 plus 1, right? So it will be 3 by 2. Okay, it will be 2 by 3 u power 3 by 2, right? So this will be the whatever your integral is. I mean, your indefinite integral is. So now substitute back the u here. So this will be 4 pi by 3. So your u will be x plus 1 by 4. So x plus 1 by 4, right? Power 3 by 2. Now you want to integrate it from 1 to 4. So then if you look at the integral, 2 pi square root of x plus 1 by 4 dx from 1 to 4 is nothing but 4 pi by 3 x plus 1 by 4 3 by 2. This evaluated at 1 to 4, right? So this is all. And I mean, I will leave it here, but you can just evaluate and simplify. If you simplify, you will get answer something like this, pi by 6. You will get 17 square root of 17 minus 5 square root of 5. Okay, you will get something like this. But for all the practical purposes, I think it's not very important to do it. Okay, so basically this 4, you will get 4x plus 1 by 4. And then you have to do some trick, and then you have to do some cancellation, and you will end up getting this. But okay, just 1 minute. I just want to make sure everything is correct, and then we'll move on. Just give me 1 minute. I just want to see it is right. Will I get 4 here? Yeah, this is right. But anyway, you just have to substitute here. I mean, I will erase it. I left it for you to figure it out. So that's not much to do here. You just substitute back, and then you will get the solution. Okay. So, okay, this is the what you do when you have the curve, which I mean, you want to find the surface area, which you're doing. I mean, you're kind of rotating it over the x-axis, Similarly, you can rotate over the y-axis. So let's do one problem where we are rotating over the y-axis. So let's solve a problem where we rotate over y-axis. So let me write a question here. So this will be our third question. So in this case, I have a function like this. Okay, so you have a function y which is equal to sorry you have okay, you have, let's say, uh, y which is equal to cube root of 3x. Okay, so now what you do is you look at the consider the portion of the curve where 0 less than or equal to y less than or equal to 2. Okay, so you just considered this part of the curve, not the every part. Now what you're going to do is you're going to find the surface area. So find the surface area. Area of the surface generated by revolving the graph around the y-axis. So last time we revolved the graph around the x-axis. Now we are doing the same thing, but this time you are doing it around the y-axis. Okay. So see here, what happens is you have the function here, which is y equal to, you are writing in some sense like this, but instead you can see it like this. Okay, so you can draw the graph if you want. So if you draw the graph, it looks something similar. I probably draw it here. Okay, it looks something like this. It looks something like this. Okay, so this is how your graph looks like. Maybe I'll draw it properly. It looks something like this. I mean, I will explain how you can visualize it. See, this function is what? This is basically, I will write the function here. This is y equal to cube root of 3x, right? So this is your function, right? But you can see it a little bit differently. What you do is you have cube root, but you take the cube on both sides. Okay, this y cube is equal to 3x. So this implies x equal to 1 by 3 y cube. Okay, so this is your function. So now what you do is you have this x-axis here and you have this y-axis here. Usually you draw the graph like y equal to f of x. So you draw like that. But instead, what you do is you just rotate it. Okay, you see it this way now. I don't know if, I mean, I cannot change the orientation here in the diagram, but what you do is you kind of see it like this is the exact, I mean, usually we draw this first and then we plot it here, right? Instead of that, you see here, okay, and for example, you forget this and you see it as a, like usually what you see as a x-axis, you see the y-axis now, and you see the other way around. Okay, and you can see that this function goes like this. Okay, so because this is basically what this is basically some cubic function, and you can see the cubic function usually goes something like this. Okay, so if you just look at y equal to x cube, the y equal to x cube looks something similar, something like this. This is the same function here, but only thing is uh, it's a little bit different. So you have to see it like in this axis first, and then so basically you rotate your how do you say, uh, you flip it around this line. Okay, so basically you flip your uh, this coordinate system, xy coordinate system, around this line. Okay, and then you kind of draw the graph and then go back and you can see it. Okay, but anyway, so what we have to do is so we have the function here, and what you have to do is you want to integrate the function from 0 to 2, right? So you want to integrate it from 0 here to 2 here. So you will get some area like this. So probably will erase it and they will draw how the area looks like. So you have get some area like this. Let's say okay. And you want to find the surface area of this particular thing. Okay. And this will be 2, and I'll just look at the area. Okay. Okay, so you have to find from 0 to 2, right? So to find from 0 to 2, you have to go all the way. Okay, so this is your 0, and let's say this is your 2. So this is the the side that you can see. The other one goes around the curve. So, but anyway, I think it will be more or less clear here. Just right here. So the other one was going. Okay, yeah. So this side was behind the axis here. Okay, but anyway, this is you want to find the surface area of this one. So the idea is basically the same. What you do is you will integrate, but with respect to this axis, you will integrate. Okay, so you write your function as here you are writing the function as f of x, right? So some function f of x. Instead of that, you see a function as f of y. Okay, so here you have the function x, which is a function of y. Okay, and you integrate this function with respect with the limit 0 to 2. Okay, so this is what we do. So your surface area is nothing but uh, integral from c to d, where this is the c. See, this is the c, and this is your d here now. So what you do is 2 pi g of y square root of 1 plus g prime of y. The same formula, whole square dx. Okay, so let's compute it here. I mean, here also there's not much to compute. So this is 0 to 2, 2 pi 1 by 3 y cube. Okay, so now you want to take the derivative of this. So derivative of 1 by 3 y cube, and you can take that's basically just y square, and you have to take another square. So if you write it down, you will get 1 plus y power 4 dy. Okay. So far so good. Now all you have to do is you just need to integrate it. Okay. So again, we don't want this 1 inside the square root, so we make the substitution again. So most of this integration, I mean, at least this problem is substitution, but not necessarily it has to be always like this. Okay, so u equal to 1 plus y power 4 we do, and then you will get a du equal to 4 y cube dy, right? So this is what you got, and when we'll probably draw the table here. So we have y here and we have the u here. So y varies from 0 to 2. And now you have to check where the u varies from. It varies from what is 2 power 4. 2 power 4 is 16. So it varies from this to 17, right? So now we look at the integral. So our original integral is integral from 0 to 2. So here we will just see 2 pi by 3. So this is y cube 1 plus y power 4 dy. So this is our original integral that we start with. Now your original integral became integral 1 to 17. Okay, so this is 2 pi by 3. And then this is 1 by 4 square root of u and u. Okay. Whereas this term is u, and these terms you can combine from here. Okay. So if you want dy is nothing but 1 by 4 and whatever this is. Okay. So basically y cube dy is nothing but du by 4. Okay. So we'll replace these two things by 1 by 4 du. Okay, now just integration is not very hard. This will be 2 pi by 12, and you just integrate. That will be u power 1 by 2, right? 1 by 2 plus 1 is 3 by 2 by 3 by 2, of course, again, and you have to integrate from 17 to 1. Okay, you just have to substitute that, and you will get the answer. So this will be 4 pi by 12 u power okay, right here this is 17 3 by 2 minus 1 3 by 2. Okay, so for all our purposes we don't need to go around and calculate the decimal. So this is whatever the answer of this is the value. Okay, so if you want you can compute the decimal also, which I have computed it. It will be 24.118 whatever the units that you have. Okay, so unit square. But I know for any reasons, I mean, we don't need it. So okay, but anyway, so what we have seen is you can rotate along the x-axis also. You can rotate along the y-axis also, and we have seen example in both cases. Okay, if it rotate along the x-axis, what happen? If it rotate along the y-axis, what happens? Okay. Okay, just give me 1 minute. I will charge my laptop. I think the charge is low. So yeah, we will meet after a minute. Okay, so far we have done the surface area and the arc length computations, and I think the reason how the formula comes was done in the class, so I'm not going through it again. But computing is basically very routine. All you have to see in this case, all you have to do is somehow you have to remember the formula. Okay, the hardest part about doing that is remembering that, and if you are good at this, then you don't have to do much. Okay, so that's all. You have to remember this formula and basically the other formula here. Where is it? Yeah, you have to remember this formula. This remembering may not be very easy, but somehow once you remember that, that's not much you need to do. Okay, and the reason why these are the formulas is I think it's done in the class. See, in the class, we all have also had this numerical integration part. So where we did the trapezoidal rule, etc. But this part also we have covered in the earlier tutorial. So I will not go into this again, since we have done already. And there was assignment in I think 2 or 3 quizzes before, and you have to. So we did it some part of it, but yeah, it was covered later in the course anyway. Okay, but this part we will skip for now because since we have already done, we don't have to do it again. So now let's move on to the convergence of the sequence. Okay. So before going to convergence of the sequence, I assume that all of you know what is a sequence and what does it mean by convergence and divergence, etc. So we'll start with the problems directly. Okay. So this So let's start with the here, which is convergence of. So convergence or basically divergence also. Of a sequence in series. Okay. So we will. I mean, we were not able to do all the theories of convergence, divergence of sequence and series, but we will do. I mean, a lot of examples. Okay. So probably I can give you the ratio test if you want, but yeah, I don't know. I don't know if it's not done in the class. I don't know if I want to go into that, but so we will do a lot of examples, etc. So that was the idea. So let's start with the definition anyway. I'll just kind of give the definition and then we'll proceed. I will not explain much about the definition, but just to recall your memory, I will just give the definition. Okay. So let's say you have the sequence an of real number. So uh, be the be a sequence. Let this be a sequence of real numbers. Okay. So we say that the sequence an converges to another real number. Yeah. So, sometimes people, write like instead of writing converges, some people say an tends to a. Okay, so this is, I mean, I'll write here. So people write, the sequence an tends to. So this is a, different way of writing it. Okay. So, and basically we use this notation. If you want, the people write this a is nothing but the limit n tends to infinity an. Okay, so this is a notation, uh, but basically what we are telling is we say the an converges to a real number a if, so we'll write here, if for all epsilon greater than 0, there exists a stage n which belongs to the natural number such that this an minus a, this has to be less than epsilon for all, uh, or we'll write the whenever. Okay, whenever is same as for all, but yeah, get no equal to. Okay, so what it tells you is, I mean, you have the a here after some stage n. So if you choose the epsilon ball here, every an is kind of lie inside this. Okay, so you can choose the epsilon, as small as you want, but you can always find the an such that after that n, every an is kind of is in the epsilon ball. So in some sense, it is telling that as n tends to infinity, your sequence are your elements in the sequence are going closer and closer to a. Okay. So once you write the definition, the first question that comes is, okay, is every sequence converges? Okay. In general, not every sequence converges. Okay. So not every sequence converges. So yeah, if you say not every sequence converges, okay. So what is the example? So easiest example is you consider this sequence. Okay, so it's basically 1, 2, 3, etc. Basically, it's a set of all natural number. Okay, or if you want to write as a sequence, you have to write an equal to n. Okay, so this is the sequence. Okay, so basically this is the sequence n. Uh, n belongs to natural number. Okay, however you want to write it, maybe let's not use this notation, but yeah, this is one of this. Okay, an equal to n, or you can use this. Okay, so if you look at the sequence, you can clearly see there is no, a after which, there is no a such that there is a, capital N such that every n is, near a, because that's not possible, right? Because your n is unbounded. After some stage, this n will be larger than a, right? Every n after that will be larger than a. So that's not possible. So what at least you can have is from this example at least what you can see is if you have a convergent sequence, then it looks like it is bounded, right? So what we can observe from here, let me write it as a theorem. If an converges, then the set an, which is bounded. Okay, the set an is bounded. Okay, I will come back and say, okay, what I mean by bounded, etc. But let's proceed with our examples. So what we have seen is we have seen a sequence which converges. Okay, which does not converge. So now can you give a sequence which converge? Okay, so this is a not convergent example. Okay, so here are more examples here. So let me write the second one. So we have a sequence which is convergent. So let's say you choose this sequence 1 by n. Okay. Now what you can see is this. I'm not going to prove it here, but I will just kind of do some intuitive thing here. It's not a proof, but I will just draw the intuition. Okay. So let's say here is a 0. So 1 by n, let's say start with 1 here, and you have 1 by 2 here, and then 1 by 3 will somewhere here, and you have 1 by 4 somewhere here, and 1 by 5 somewhere here. So basically, you're going closer and closer, closer and closer to 0, right? So this sequence converges to 0. Okay, it requires a proof, but at least when you look at the diagram and when you see it, it kind of goes to 0. Okay. Okay, now what about any other sequence? So we have seen a sequence which is kind of not bounded; it is kind of keep on increasing, and we have seen a sequence which is convergent. But let's look at another sequence here, which is quite interesting one. So this is let's say minus 1 power n. Okay, if you look at the sequence, what it does is uh, when n is equal to, let's say, start with 1. Okay, so you have a 0 here, and you have a 1 here, and you have minus 1 here. So when n equal to 1, the sequence kind of start from here, right? So when n equal to 1. And when n equal to 2, it goes here. So but when n equal to 3, it comes here again, right? When n equal to 4, it goes here. N equal to 5, it comes here. So this sequence, if you look, it jump from here, 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 here. It is keep on jumping, right? So it's kind of oscillating. This kind of sequence are called oscillatory sequence, and this sequence also does not converge. Okay, so we introduce a new terminology here. You have the sequence AN. We say the sequence AN diverges if it does not converge. Okay, so but here I have to just tell some people define divergence a little bit differently, but for me uh, divergence means it does not converge. Some people say divergence means it has to goes to the limit is uh, infinity, but yeah, I don't know how standard it is. For me, the at least when I say diverges, it means it does not converges. Okay. Yeah, but it depends. Okay, but it depends on which book you follow, any standard book. Okay, so that's something I want to tell here. uh, and we I will just look through some theorems here. So some standard theorems which you might have done in the class. So if you have a limit of a sequence, so what in the definition what we did is, see, we say this sequence converges to a real number A if such and such a property happens, right? That means that you have to have the sequence is given. Now, what you have to do is you have to find there has to be an A which exists with whatever the property it is. Then you say this A n converges to A, right? Now the question is, can there be multiple A? Okay, so let's say a function, this sequence converges. Can it converges to two different limit? Okay, so this is the limit of this sequence, right? Can there be more than one limit? So this theorem says that the limit is unique. Okay, so limit of a convergent sequence is unique. Okay, of course, if your sequence does not converge, then you would not talk about the limit itself. So, I mean, there's no need for thinking about whether it's unique or not, right? But of course, even a sequence like this, which even though it converges, does not have a limit, there is a notion called the limit points, or there's something called the subsequence, etc. So there is a theory going on here. Okay, the function. Okay, let's say this example you take. This is not convergent, right? But on the other hand, if you just look at the odd terms of the sequence, okay, which will be minus one, minus one. So your sequence will be minus one, one, minus one, one, minus one, one, something like this, right? Now you look at the only the odd term of the sequence, which is minus one, minus one, minus one. So this odd term sequence is basically this, right? And if you look here, this is convergent. Okay, and similarly the even terms are just one, 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 and these are also convergence. So this directly tells you, okay, even though my sequence is not convergence, but instead of taking all these things, if I can just choose a I mean, if I don't want to take everything, but I take only some element in the sequence, okay, and that is called subsequence, and the subsequence can converge even though your sequence is not converging. Okay, but there are theorems about the subsequence and sequence, but when your sequence is converging, every subsequence also converges and it actually converges to same limit. So that's not a problem. So but at least anyway, let's not go through the subsequence right now. What we have is, if you have a convergent sequence, then the limit is unique. Okay, this also I will not prove it. It's one of your assignment problems. So I mean, give a try. Okay, try to prove it. Uh, so I'm not going to prove it here. So what we do is, let's start with the. Let me define what is the boundedness. Okay, so we see a sequence. So we have the sequence an. We say this sequence an is bounded if there exists an r greater than 0, such that modulus of an is less than r for all n. Okay, and we say a sequence is not bounded. Sorry, we say a sequence is unbounded. Okay. So we say it's unbounded if an is not bounded, if it is not bounded. Okay. So if you want to imagine, it looks like this. So you have, let's say you start with a 0 here, and you have the plus r and you have the minus r. Okay. So a bounded sequence means you have this multiple points here, but all of these points are somehow between these two, so here you can an you can have an plus 1 here and maybe an plus 2 here, an plus 3 here, whatever it is. Uh, but all of these points are between this r and minus r. Okay, so here one can say, okay, well, what if I put instead of strictly less, why not less than or equal to? It doesn't really matter, uh, because if you define with less than or equal to, it's same as less than only, right? Because if it is true for this, then you can add a plus one, and that is so. If you have two definitions, one is with less than or equal to, and another is with less than, they are basically the same. Okay, you can try to see why it is true. Okay, so you can also do like this. It doesn't really matter, uh, but I will just keep like this. So because some books use the less than or equal to, but it's not really necessary. Okay, so maybe we will also add a less than or equal to, but yeah, again it's doesn't matter. Okay, so basically what it says is function is bounded means it is kind of all the function lies between these two. Okay, for example, if you look at the natural number sequence in here, this is not bounded, right? Because you have one, you have two, you have three, and so on. Let's say you have one, two, three, four, and you keep going. At some point, you will be there will be n which is greater than r. Okay, so natural number is not bounded. Okay, so what about the sequence 1 by n? 1 by n is bounded, right? So this is 1 by n. So this is 1 by 2, etc. So you go like this, and you will bounded by 0 here and bounded by 1 here, right? So, but if you want to say bounded, you can choose, minus 1 to 1. Okay, so it is bounded by from minus 1 to 1, because you kind of want the same r, right, on both sides. So, okay, so that this is what I mean by the sequence is bounded. So what we have seen is if you have convergent sequence, it kind of looks like it is bounded, right? Because if it is not bounded, how after a stage every element is around this this limit a. I mean, this is not possible, right? Because your sequence is unbounded. It keeps on going up like this, right? So at least you need a boundedness. So that is the theorem here. We already wrote the theorem, but I will write it here again. We will use the different color. So the theorem says that every. So maybe I will just write the theorem here. So this is the theorem here. Uh, so I will write the proof looks like. Okay. So since we have introduced the epsilon delta notation, probably I'll just do one problem with epsilon delta. I may not do much uh, using this, but at least I will do one problem so that you kind of get the idea of, okay, what exactly is, I mean, how to use it in case if you need to use it. Okay, most likely we will not use it because we will just use the algebra function. I mean, we know certain limits for which you have to of course come to here and use it. After that, mostly we going to look at the algebra of limits, and then it's like similar to calculus. We have the same algebra of limit, and then we are going to use the same thing again, more or less most of the time. But whenever something you cannot do like that, then you have to come back to the definition. Okay, so let's prove it. So what we are going to prove is if your sequence is convergent, uh, then it is bounded. Okay, so that is what we are trying to prove here. So let's see. Let an be a convergent sequence. Okay, so convergent sequence. Let's say an converges to a. Okay, so what does this tells you? Then so probably we'll go here, and you can see here. So that means for any epsilon, there exists a natural number such that an minus a is less than epsilon whenever n is greater than or equal to n, right? When it has to happen for every epsilon. So let me, for whatever the purpose I want, let me choose the epsilon to be 1. Okay, because I just need to found one bound, right? It can be anything, so I can choose whatever epsilon I want. I just need to get one bound. Okay, let's choose. There's nothing very important about the choice of epsilon equal to 1. I mean, it can be anything you can choose. I choose 1 because it makes the life, I mean, it's easy to compute. So then what happens, for this choice of epsilon, there exists a natural number n belongs to the natural number such that this an minus a is less than 1 whenever n is greater than or equal to n. Okay, so this much we have. Okay, now what do you do? Okay, so what you do is here you apply the triangle inequality. Okay, so if you apply the not exactly, so you have to apply a similar inequality here. Not exact triangle inequality, but like reverse triangle inequality. Okay, so this is like an minus modulus of a. So this is less than or equal to an minus a. Okay, so this is a standard inequality which is known if you have a mod x minus mod y. So this will be less than or equal to mod x minus y. Okay, this is a standard inequality. I mean, we also have done it once. In one of the previous tutorial, we talked about it. So I'm not going to uh, do it again. Because there's no point in repeating it, which we already done. So this will be less than 1, right? And this 1 is basically your epsilon, but yeah. So from here you observe now. So this tells you mod n uh, is less than 1 plus mod a whenever n is greater than or equal to n. Okay. So I will, okay, now what is the consequence of this? Okay. So n is greater than or equal to not natural number n, just n. So this is that stage, right? After this stage, uh, you have this equality. So what does it tells you is, so let's say I have uh, a here, and let's say you have mod a here, and you have mod a plus 1. Okay. So what it tells you is a mod of this an is less than or equal to mod of a, so 1 plus mod a, right? So that means your an will be lies between minus of 1 plus mod a to 1 plus mod a. Okay. So all your an is kind of lies between this interval. Whenever your n is greater than or equal to n. So basically, after this n, everything is kind of lies between some domain. Now what remains is basically what happens when uh, your n is less than or equal to this n. When n is less than, strictly less than this n. Okay, so that we have to take care of, because after n everything is here does not mean a1 can be here, right? So that we will take care of now. How do we take care of that is we define the capital M, which is basically we start with mod a plus 1, but then we have to take care of the a1 to an also, right? So we will choose those also. So we take a1, a2, mod of a2, etc., mod of an minus 1. Okay, so I will probably write it below. Minus 1. Okay, so we take the maximum of so this is basically maximum of all these numbers. Okay, so by choosing the maximum of this, we just make sure every number is less than so all this a1, a2, etc., everything, the modulus of this will be less than m. Okay, so that we will make sure, because just by this we can do for all n which is greater than or equal to n, but now we have to look at the other n's, and that kind of comes by choosing the maximum when you have to kind of now taking care of the other elements also. Okay, so now by the definition you can directly see that then, so you have to use this definition together with this fact. You can clearly see that you have this mod n, this is strictly less than m. Okay, this is true for all for every, I'll write for all. Okay, for all n in n, and you're done, right? So this tells you that this means that your sequence n is bounded. Okay, so now the question is, okay, I have a sequence is bounded, so what I know is convergent implies bounded. So we have now the question is, okay, is the reverse question correct? Does the bounded implies convergent? And of course we have the example, right? There's a classic example of -1 power n. It's a bounded sequence. So we'll write here, probably we'll say no, converse is not true. And this example pretty much tells you that the converse is not correct. Right? Okay, so after this, the main tool that we can use is basically the algebra of limit of convergent sequence. So I will try to do as much theory as possible. Maybe I will not do more proof. I will just do how to solve the examples, because that's mostly what the tutorial session is about, at least now, for now. But for not by any means I'm not doing it exhaustively, because there is so much things to be covered. So I will can do within the time limit. Okay, we have maybe 40 or 50 minutes within which we'll try to do whatever we can do. So we'll look at the algebra of convergent sequences here. Okay. So suppose you have these two sequence. Okay, you have the sequence an, and you have the sequence, let's say, bn, be a sequence of real number. So whatever we did for I mean, we have some algebra of limits for the functions also, right? Limit of functions also, it's the same kind of thing, so holds here. Okay, so there is not much difference here. So let's say my limit of limit n tends to infinity of an is, let's say it goes to a, and we have limit n tends to infinity of bn, let's say this goes to b, and we have, let's say, r and s we some real number. Maybe we don't need it for now, so let's do it. Okay, so where this a and b is a real number, of course. So then you have the same kind of thing, so we'll write it here. So the first one is the limit of limit n tends to infinity, or an plus s bn is nothing but ra plus sb, and this is true for all r and s belongs to r. Okay, so you can take any linear combination of an and bn, and your limit is kind of the same. Okay, So this is sometimes people called as a linearity rule. If you want to, you can write it. Then, and then, yeah. So the second one is you look at the limit of n tends to infinity. So you have an and bn. You do it. This is nothing but ab. Okay. So this is basically the product rule. Uh, and similarly, there are other rule like a quotient rule is there. We'll do that also. So you look at limit n tends to infinity, an by bn. To define the bn, I mean, of course, to define the sum, the bn has to be non-zero. Okay, at least bn has to be non-zero after some stage. Okay, then you can define this. Yeah, but of course, this number does not make sense if you know if your bn is zero. Okay, so that you have to be careful about. So this will be equal to a by b, and this is also there provided if b is not equal to zero. Okay, if b is equal to zero, then this doesn't make sense. Okay, a by c doesn't make sense. Okay, so this is the quotient rule, and we have some square root rule, etc. So you look at the limit n tends to infinity. Mth root of an. This is nothing. This is basically mth root of a provided mth root of an defined for all n and mth root of a exists. Hey, why do you care about whether it's defined or not? Because if you take something like square root of -1, I mean, you can say it's an imagined number, but it's not a real number, right? So inside the domain of real number, this square root of -1 is not defined, okay? So whenever it is defined, the nth root exists in real number, and here also it has to exist, then you have this algebra of limit. Okay, otherwise it does not work. Okay, the proof one can do it, but I will just skip the proof because there is not much. I mean, we gain by proving it. The simple case of this one is where this an is equal to 1. Okay, so when you have an equal to 1, what you have is the following. I'll write here. It is basically a simple case of the below one. So we have a limit n tends to infinity bn. So let's say this tends to b, and you have this b not equal to 0. Then you have the something n tends to infinity 1 by bn is equal to 1 by b. Okay. Of course, this bn's are also has to be non-zero. Okay. So this is basically sometimes called the reciprocal rule. Of course, the names are not really that important, but it just kind of tells you, what exactly is happening. Okay, so here you have to kind of take the reciprocal of this and reciprocal of bn, and the limit also kind of get reciprocal. So it kind of just tells you uh, what is happening there. But yeah. So let's try to do some problems here, maybe. Let's see which problem. I mean, I have a lot of problems, but let me try to uh, choose some good ones. Okay, so probably I will create some problem instead of doing it. I mean, I have some hard problems which you will do, but I also want to do some easy problems before we go into hard problems. Okay, so let's look at this one. Okay, for example, let's look at. We'll start with the easy one. N plus 1, let's say, divided by n square plus 3. Okay, and you want to find the limit n tends to infinity. So this is a question. If you want, you can type the answer, which you might do it very quickly. 0, right? Yeah. It's obviously very easy problem, so you can always do it. So idea is what you do is you start with the n plus 1 divided by n square plus 3. Uh, you divide the both the numerator and denominator by n. Okay. Now when you do it, what you get is you will get 1 by n divided by uh, here you what you get. Yeah, you will get n plus 3 by n maybe. Okay, maybe you divide both by kind of like by n square, because that would be easier to do. So this will be 1 by n plus 1 by n square divided by 1 plus 3 by n square. Okay. Now you apply the product rule. I mean the quotient rule. So when you apply the quotient rule, what you do is the first term here, this goes to 0, because each of the terms goes to 0. So the first term goes to 0 above. And below you look, this term goes to 0, but this will not goes to 0, right? So this will goes to basically goes to 1. So you have 0 by 1, which is 0. Okay. So this was, let's say, the easy example. Let me look at some more easy examples, and then we will do little hard ones. Okay. So let's look at a sequence like this, where I have, let's say, an is nothing but 1 plus, uh, okay, let's say I have something like this. Okay, 1 by 2 power n. Okay, now what about this? So yeah, this is one, right? Why? Because you apply the algebra of limit. This will be so if you look at the limit of an, this is nothing but uh, 1 plus limit of 1 by 2 power n. Okay, so here you can see the 1 by 2 power n. If you look, this 2 power n kind of goes to infinity, right? So as a whole, this terms goes to 0. Okay, but one has to prove it. Okay, yeah, it's not all that easy, but you have to prove it. But what we will do is we can use this kind of squeezing theorems, etc. We will later see how we can do it. Okay, this we will do. Come back and we will prove this limit. Okay, so this goes to 0. So this means this particular thing goes to 0. So totally you have the limit of an equal to 1. Okay, so we will come back to this. Okay, we will prove later. Okay, but this requires a proof. I mean, although it's obvious, looking obvious, but yeah, requires a proof, and we'll do the proof also. It's not very hard to do. Okay, now I will do maybe a little bit of more easy example, and then we'll go to something interesting. Okay, so the third example is sine n pi, n pi, let's say, or n pi by 2 will do. So what about this one? So it's convergence or divergence. So it's diverges, right? So why? Because you write the sequence first. So this is a sine, first term is sine pi by 2, and you have a sine, I mean, you have 2 pi by 2, which is uh, basically sine pi, and then you have a sine 3 pi by 2, and then you have a sine 2 pi, etc., right? And it kind of keeps going. So here, if you look, sine pi by 2 is basically start with 1, right? Sine curve is how much? Yeah, it goes to 1, and then it goes to 0, then minus 1, then again 0, and then 1, 0. So it goes like this, right? So if you want, you can just draw it and see. The sine curve goes like this, and this n pi by 2 is basically this. This is pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, 5 pi by 2. So the sequence kind of oscillates like this. Okay, it oscillates. The terms that comes in the oscillations are 1, 0, and -1, and it will keep repeating. Okay, so this sequence is diverges. Okay. So these are some easy examples. Now let's try to do yeah. But before going that we will do a theorem. I will not give the proof, but we will at least write the theorem. It's very useful theorem. So when we do the limit of a function, I have also mentioned this theorem, but at the time I didn't give you any example. But anyway, the same kind of theorem appear here and here. Let's say we give quite a good amount of examples. Okay, so let you have this sequence an and you have the sequence bn. You have three sequence, right? An, bn, and cn. Okay, be three sequences such that an is less than or equal to bn is less than or equal to cn, and then okay, I mean this is this holds for all n. Then you have the following. Just give me a minute. Wait, I mean, see, when I write this holds for all n, this is quite quite stronger condition, but you don't actually need this much stronger condition. So all you need is it holds for all n greater than or equal to some n, because when you do the sequence, it's always what matters is something called the tail of the sequence. I mean, some people use the terminology tail of the sequence, which is you start with a1, a2, and similarly you keep going. Okay, so what matters is what happens in the after some stage, whatever happens, till it goes to infinity. So the what I'm trying to say is what happens with the first few times doesn't really matter. Okay, so what matters is what happens when it goes towards the end. What happens? So if you kind of draw an animal, like the head start from a1 and etc. Then tail is basically what remains if you take out some of this, some of the part which you may consider as a head. Okay, but anyway, that's something. Yeah. So basically, let's call the tail of the sequence, which is basically the sequence, but you kind of take away a few terms, finitely many terms from that. So basically, this is called the tail of the sequence. Okay, so you're looking at the an, but where n is strictly greater than or equal to n. Okay, so this is called the tail of the sequence because first few terms you kind of skipped it. Okay. So and that is all that matter when you want to look at the convergence, because the first few terms really doesn't matter. And when I say few, it can be however large. It can be trillion. It can be 100 trillion. Doesn't matter, because any number is a finite number. So yeah. So and for some n. So basically, what I'm trying to say is there exists a natural number n, such that after that natural number, you have this kind of setup. Okay. So if the limit an and this limit n tends to uh, infinity cn, if these two limits are L, then what you have is then bn is L. Okay. So this is what you have. And again, you have Okay, this is one conclusion, but you can also do some kind of limit thing for diverges also. So you can say if Bn tends to infinity, then Cn tends to infinity. So infinity. Okay. Also, if Cn tends to minus infinity, then Bn tends to minus infinity. Okay, so these are some kind of a comparison, because if you can see this Bn goes to infinity means on this Cn is always greater than Bn, so Cn also has to go to infinity. Similarly, Cn goes to minus infinity, but Bn is smaller than Cn every time, so Bn also goes to minus infinity. So that's some kind of a comparison. I mean, you forget this, which is comparing these two. That is this two thing. But what the actually interesting one is when both of these converges, and it converges to, let's say it converges to the same limit, then the middle one also converges and it converges to the same limit. Okay, remember this, because this is going to be very helpful. Okay, let's come back to our problem here, where we want to evaluate 1 by 2 power n. Okay, so let's look at this problem. So we want to find that the limit of 1 by 2 power n. Of course, you can use the epsilon delta and prove it. So is what? So this is the question, right? So let's try to do here. So what we know is, we know this, right? N is less than or equal to 2 power n for, let's say large n. Even for n equal to 1, this is true. Okay. This you can prove it. If you don't know how to prove it, you can use calculus also to prove it. Okay. So, but anyway, basically, if you want to prove it, you can choose the x minus 2 power x, and then prove that this is kind of less than 0. Okay, uh, not necessarily less than 0, but yeah, I mean, take x minus 2 power x, and let's say prove this is a decreasing function. Okay, so if you can prove this is a decreasing function, all you have to do is you evaluate at n equal to 1, and after that this function, I mean x minus 2x is a decreasing function, and you will get this inequality. When that's something, if you want to prove it, you can prove it, but I will assume this inequality for now. Okay, so the multiple ways to prove it, one is to use the binomial theorem. You can use you can write this as 1 plus 1 power n, and then if you compute the binomial coefficients, uh, okay, maybe I'll do this. See, I'm just telling you there are many ways to prove it. This you might find it interesting. If you look at 1 plus n, so this is you have to use the binomial theorem. Okay, so this is 1 plus n choose 2. So what is this? Just 1 minute. It has to be n choose x, right? So in this case, it is nx plus, sorry, it is n plus something, it goes. Plus some terms will come. Okay, so maybe I will write the binomial theorem for you here, and you can just observe that this is true. I'll just 1 minute. I mean, I just again wants to just look at what are the terms there. I mean, I just want to look at the hypothesis. I don't want to write it wrongly. Okay, I will write here. Probably we will use the binomial theorem many times, so I will write the binomial theorem here. You just remember this if you don't know it. Okay, so the binomial theorem says the following: if you have x plus y power n, where I mean in this case this n is a non-negative integer, so let's, for our sake of argument, we'll just take n belongs to natural number. Okay, I mean you can have this as some fraction. I mean, yeah, there are some generalization of this, but for all that we care about, we don't need enough this. Okay, you have a generalized binomial theorem, which is kind of given by see, this binomial theorem is known for a very long time. Okay, But then there is Isaac Newton came, and he kind of introduced a thing called generalized binomial theorem, where this n belongs to natural number is not really needed. You can put some, you know, what is this? I mean, you can put some rational number also. But for our purposes, we don't need that. We'll just use the direct normal binomial theorem. If you're interested, you can just look at something called binomial series. You can look at that. But whatever we want to do, it doesn't matter. Okay. So this is, I will write it in the summation notation. I hope you can understand the summation notation. 1 to n choose k, x power n minus k, y power k. Okay. So this is the binomial theorem. So now you write for 1 plus 1 whole power n. This will be n equal to 0. You have to start. 0 choose, you know, sorry, k equal to 0 to n, right? Yeah, I think, yeah, k equal to 0 to n, not n equal to 0 to n. That does not make sense. Okay, so k choose 0 is just nothing but just 1, and you have to see up also. So yeah, and here you both your x and y are 1, right? So you just have to apply it and see. Okay, so this will become 1 plus n plus something, it will go. Okay, you can try to see it. Just n in 10 plus 1 will come again, and etc. Okay, because see, this x and y are basically 1 for us, right? So this will go away. All you have to write is in our case, if you want to, I can just write it here directly. So this will be summation k equal to 0 to n, n choose k. Okay, and this, if you want to write, this will be just 1 plus n plus n into n minus 1 or n plus 1 something. I don't exactly know. Okay, yeah, n minus 1 by 2 something, and then it will go. Okay, but anyway, this is not yeah, and but one thing what you can observe is okay, maybe I will not write first time, I'll keep the second time, I will just write as n choose 2. Okay, n choose n. So this is what we have, but here you observe this term is a positive number, right? Why n choose 2 is positive? Or for any purpose, let's say why n choose k is positive. I mean, you can give a one line argument, because n choose k is basically number of ways of choosing k elements from n elements, right? So if you want to choose number of ways, the number of ways can be either a 0 or a or a positive number, right? You cannot have a negative number of ways of choosing it, right? Because what we are doing is basically we are doing some counting, right? And anything that has to do with counting is actually a 0 or a natural number, right? So this term is either a 0 or natural number. Okay, so this is one of the proof that binomial coefficients are a natural number, because it in some sense tell you as a number of ways of counting something, and the number of ways of counting something is I mean, you cannot have a negative ways of counting it. Either if it is there, if object is there, then it is a 1. If it is not there, then it's a 0. I mean, it cannot be negative, right? Okay, anyway, these numbers are positive, right? So you have this and this. So this clearly gives me an inequality 2 power n is greater than or equal to 1 plus n. Okay, how I get the inequality is I just take this and trimmed this. So if you look here, this is greater than or equal to 1 plus n. Okay, and I just remove these terms and you will get it. So this is what I am getting here. And from here you can directly use, once you get this inequality, this is a very child play. So what you get is 2 power n is greater than or equal to n. Okay, so this is one way to do it. Just use the binomial theorem and you can get this. Or if you want, you can use calculus also and you can prove it. Okay, it's not but I am not going into the calculus way, although it's a calculus course, we should have done in the calculus way, but anyway. Okay, but let's go here. So what we have is n is less than or equal to 1 is 2 power n. Then the reverse you can tell 1 by n is greater than or equal to 2 power n. Okay, or in other words, you have 1 by 2 power n is less than or equal to 1 by n. Okay, so this much we have. Now what you also observe is this number is always positive because 2 power n is positive, 1 is positive, so the quotient is a positive number, right? So you have 0 less than or equal to 1 by 2 power n less than or equal to 1 by n. So this is what you have now. Okay, so here is the setup for the squeeze theorem. So this is also called sandwich theorem or squeeze theorem, whatever, however you want to call it. Now you just look at the limit of this. Okay, so the limit n tends to infinity of 0. This is a 0, which is equal to limit n tends to infinity of 1 by n. Thus, you have limit n tends to infinity of 1 by 2 power n is also 0. Okay, so this you're just using the squeeze theorem and you get it. So when I did said in the calculus this very interesting thing, at the time I was not able to give the example, but you can see in most of the thing in the sequence and series you are going to use this theorem, and it's going to help you really good. Okay, anyway, we have done this much, so let's do at least one or two interesting examples. Okay, and there's something called monotone convergence theorem. Probably we'll just at least state the theorem because it will be very useful. So monotone, or at least you can go and look at these theorems. Anyway, when you study, you will study it. But this theorem is going to be very useful sometimes. So what the theorem talks about is you have a sequence xn. So which is a monotone sequence? Let xn be a monotone sequence. Let me write. I will write for monotonically increasing, but you can write for monotonically decreasing. Okay, monotonically increasing function. So what do you mean by monotonically increasing function? That means an is less than or equal to an plus 1 for all n belongs to n. Okay, so it is keep on increasing function and is bounded above, and then an converges. Okay, so similarly you can say for a monotonically decreasing function, but in that case you need to have a bounded below. Okay, so it converges, but one can also say where it converges. You can say this an actually converges to the supremum of this set A. Okay, and the supremum exists actually. The supremum exists because uh, it is bounded above, right? When it bounded above, that means there is upper bound. Not supremum. Just give me a minute. Yeah, so there is upper bound. So that means there is a least upper bound, right? Supremum is basically the least upper bound. Okay, but anyway, I had some problem about this also, but I think possibly I will not. I will skip those. I will do at least one or two interesting ones so that it will be helpful. Yeah, I will do this one. Yeah. So probably I'll write two, and we try to finish it in let's say 15 minutes or something. We'll finish it. Yeah. So first problem, what we do is we do find this one limit n tends to infinity. These are some standard tricks people use it. And of course, there are so many standard tricks when you do the jam exam, etc. But I only remember few of this, and I will just do some of this. Okay. Okay. So let's say first one is this one. Second problem is second problem is a little bit hard one. We will do this. Limit n tends to infinity, a power 1 by n for a greater than 0. So this we do, and if you have time, we will do the other one also. So limit n tends to infinity, n power 1 by n. Okay, we do these things if you have a time, but if you want the proof of this, you can always find it in the Rudin's book. On it's called the Principle of Mathematical Analysis. In case if we can not able to do it, and anybody wants to look at it, you can look at it. But the proofs are beautiful, but let's try to prove one by one. At least the first one is quite easy. So what you want to do, I mean, it's not quite easy if you don't see it, what is happening. Can you able to see what to do? If you have seen such a problem, then it is not very hard to see it. But if you don't see it, it's not that easy. So first thing you can observe is you can observe 0 less than square root of n plus 1 minus root n, right? Because n plus 1 is always greater than n. So if you take the square root also, that inequality is kind of preserved, right? So this much is okay. But now if you want to do apply any squeeze theorem or something, then you have to get the other side. But from here, where you go? Okay. But if there's just a simple trick, and if you know the trick, it's not that great. But when you don't know the trick, it's not that simple also. Because I remember at some point I was doing this problem and I didn't find it that easy. But then one of my friends say, you just have to do this. For some days I used to wonder, okay, this guy is so great that I couldn't do it for a few hours, and he just told it in a second. But later I just realized. I mean, he just told me that he has seen it before. So it's very simple if you have seen it. Okay. So this is n plus 1 minus root n. You have it. Now what you are going to do is you just multiply and divide by this term. Square root of n plus 1 minus plus n square root of n. It's very, very, very standard trick if you know, if you have seen it already. Okay. So now you kind of come up with the a plus b whole, a plus b into a minus b setup. And here you can clearly see this. You apply the formula of a square minus b square here. So this minus n by square root of n plus 1 plus 10. Okay. Now that's all. Your life became very easy. Okay. So this will be 1 by square root of n plus 1 plus square root of n. Okay. Now what you do is you do some estimation. You can see that 1 by n plus 1, the square root of n plus 1. So you estimate this and put it square root of n plus square root of n. Okay. The reason is simply because n plus 1 plus square root of n is kind of greater than square root of n plus square root of n. So if you take the reciprocal, what you get is n plus 1 plus root n is less than or equal to 1 by 2 root n. Okay. 1 by 2 root n. Okay, now you can clearly see this guy goes to 0, right? And we have already observed here also, you have this guy. So let's write all of this. So now we come up with the setup of a squeezing theorem. Square root of n minus 1 minus root n is less than or equal to 1 by 2 root n. And both of this goes to 0. This converges to 0. This converges to 0. And thus just to 0 by sandwich theorem. So it's very, very useful. Yeah, you just have to set it up properly. Once you set it up, it makes your life very, very easy. Okay, maybe I will leave one exercise which I may not have time to do it. It will be very easy. I mean, not, yeah, you can see it. So probably find the limit of limit n tends to infinity, cos n square by n. Okay, and the answer is, if you want to look at the answer, you'll just write it's 0. But you have to figure out. Okay, so basically this cos n square is bounded. You just have to use somehow how it is bounded. Okay, it's bounded by -1 and 1, right? So make use of it and you will get it. Similarly, if you look at limit n tends to infinity, sine n pi by n, if you look, or let's say sine n by pi by 2, because we looked at sine n pi by 2, uh, but now if you put a n below, and this will, this will be 0. Okay, so keep this as exercise. These are very easy problems. Just you have to apply the squeezing theorem and you will get it. So let's do this one at least. This is interesting. This will be little bit hard, but not too hard. Okay. So we will deal with the two cases. Okay. So the case one is a is less than 0, and your case two is a is greater than 0. Uh, but I will do that later. Okay. So what happens if a equal to 1? A equal to 1. Okay. The claim is this is equal to 1. Okay. So when a equal to 1, this is 1 by 1 power n, and that is just 1, and there's not much to prove here, right? So when a less than 0, we'll try to prove it first. So when a is less than 0, okay, just give me a minute. Okay, we will prove when a is greater than 0, yeah. Because, yeah, the reason is we are going to use the binomial theorem, okay? So it will help us if a is greater than 0. So when a is greater than when a is greater than 1, not 0. Sorry for making so much error. So when a is greater than 1, you look at a power 1 by n. This is also again strictly greater than or equal to 1. I mean it's strictly greater than 1, but you can write greater than or equal to 1. Maybe I'll write strictly greater than 1. But it doesn't matter anyway. Okay. So then I write a by 1 by n is nothing but 1 plus some xn. Okay. And this xn is a sequence of non-negative real number, where xn belongs to R we have, and xn greater than or equal to 0. Okay, so this much we have. Now we apply the binomial theorem here. So okay, where you want to apply the binomial theorem? So you have this term, use this, and then you will get something like 1 plus x power n. Okay, so I just changed it. Sorry, xn power n. Now here we are going to use the binomial theorem 1 plus nx. So this part is basically binomial theorem. Okay, so it's basically whatever we did here. Where is this? Yeah. So here we did, right. We truncated. I mean, we just took the first two terms and then left the rest, right? And the same thing here we are going to do it. Where am I? Yeah. So 1 plus nx. So this much you have. So what you have finally got is a is greater than or equal to 1 plus nx. Sorry, nxn. Okay. From here, somehow we have to, translate everything to, how do you say? Yeah, you translate everything back to a. You don't want this n here, and somehow you want to avoid this xn here. So let's try to do that. And how do you do that? Okay, so let's see here. So we have 1 plus n xn is less than or equal to a. So this implies that xn is less than or equal to a minus 1 by n, right? But what is xn? So xn is nothing but a power 1 by n minus 1, right? So you have a power 1 by n minus 1 is less than or equal to a power a minus 1 by n. Okay, so this much we have. Okay, and look at the first equality here. Okay, what does this tells you? A power 1 by n minus 1 is greater than or equal to 0, right? It tells you this much. So this is greater than or equal to 0. Okay. Now what you do is just apply the squeeze theorem. Apply the squeezing theorem or sandwich theorem. I will just look at the spelling of it. I don't want to write it wrongly. When some people call it the sandwich theorem, it's the same thing. SQUEEZ is theorem. Okay, so if you apply it, you can see this term goes to 0, this term goes to 0. So that means limit n tends to infinity, a by 1 by n minus 1 goes to 0, right? I mean, this is equal to 0, let's say. But now you just use the algebra of limit, and you will obtain that limit n tends to infinity, a power 1 by n minus 1. So here it's a whole thing. Here it is this is equal to 0. So that implies, I mean, it gives you whatever you want, right? I mean, take the one to the other side, and what you got is exactly what you want to prove it here. So, okay, now what you proved is for A is uh, strictly greater than 1. I mean, greater than 1 is fine, but strictly greater than 1, at least we have done it. What if A is less than 1? Okay, if A is less than 1, then what you have is 1 by A is greater than 1, right? Okay, so if A is less than 1, what you have to compute is you still have to compute A power 1 by n, right? So what you have to compute is A power 1 by n we have to compute. But A power 1 by n I write a little bit differently. I write it 1 by A power 1 by n. Okay. Or I will write like this 1 by A power 1 by n. Okay. So this is the same thing. I'm just writing it little differently, but it is the same thing. Or okay, maybe I'll put the 1 by n above. This will be helpful. Okay. But now if you look here, 1 by A, since A is strictly less than n, 1 by A is greater than n. But you come to the previous case. Okay. If you just look at the denominator, so denominator goes to 0 or tends to 0. Let me write tends to, not goes to. Sorry, tends to 1, not 0. Thus, limit A power 1 by, sorry, A power 1 by n is nothing but a limit, 1 by limit 1 by A power 1 by n, which is equal to 1 by 1, which is 1. Okay, so that's the simple way to do it. But yeah, probably this may not have time, but the idea is the same as the above one. What you have to do is again you are going to use binomial theorem, and you are going to use the squeeze theorem, but instead of here I can get it by just by taking the first two terms of the binomial theorem. So I just took the first term, but the other one you have to do, it's little complicated because you have to take the third term and leave the second term because it's going to somehow help you. But yeah, the proof you can read from here. It looks almost the similar. You just need to use binomial theorem and do little bit of manipulation. That's all. Okay. Okay, we will stop now, but I think more or less the interesting theorems that you might need for your assignment is just the monotone convergence theorem, and you can use this sandwich theorem or squeeze theorem. Okay, so this will be very useful, and the rest are a little bit, 1 by what is the limit of 1 by n, and when you have a sine x or something. Sorry, yeah, sine n pi etc. This kind of small things you needed. After that, it's more or less uh, okay. Okay, we will stop now. If you have any doubts, you can ask me. Otherwise, we will end the session. Okay, if there is no doubts, then we will end the session. So we will have the last lecture on next week, and I think we are not taking any extra lectures. I mean, we can take extra lecture if you want, but so I'm not taking any extra lecture. So our last lecture is on next week. So let's see. Okay, and all the best for your exams. I think it's going to be there soon. So yeah, good luck with your exams also. Okay, see you then. Bye.